61,000 kilometers per hour. That is how fast Voyager 1 has been flying for nearly 50 years. It has crossed less than 1/1500th of the distance to the nearest star. Most people believe reaching another star is simply a matter of building better engines. It is not. When physicists calculated what happens at 10% the speed of light, they discovered that empty space itself becomes a weapon. Tonight, you are going to understand why interstellar travel may be physically impossible. Not one barrier, a chain. Let's begin. Every civilization that ever looked at the night sky asked the same question. What is out there? The Polynesians navigated thousands of miles of open ocean using nothing but stars and wave patterns. The ancient Greeks imagined celestial spheres carrying points of fire across a dome of darkness. Chinese astronomers recorded supernovae invisible to the naked eye and wondered what forces could make a star explode. Aboriginal Australians read the dark spaces between the stars and built stories from the shape of absence itself. Every culture, on every continent, across every century, stared upward and felt the same pull. The stars were calling. Humanity wanted to answer. That desire never faded. It sharpened. Modern science inherited the ancient longing and added something dangerous to it. Precision. We learned to measure the distances to stars. We calculated the energy required to reach them. We designed theoretical spacecraft on paper and simulated their trajectories on computers. We identified specific destinations, specific worlds, specific atmospheres that might harbor biology. And the numbers that came back from all of this precision were not merely large. They were a different kind of large, a kind that breaks the relationship between ambition and possibility. The dream of reaching another star is not a fantasy born from ignorance. It is a desire that grows stronger the more we understand. Astronomers have confirmed more than 5,000 exoplanets orbiting nearby stars. Some sit in habitable zones where liquid water could exist on rocky surfaces. In 2026, researchers identified 45 rocky worlds as top habitable zone targets. With especially promising systems, including the 7-planet TRAPPIST-1 system roughly 40 light-years away and Proxima Centauri b at just 4.24 light-years. The James Webb Space Telescope is analyzing the atmospheres of these worlds right now, searching for chemical signatures that might indicate biology. The targets are real. The destinations exist. The question has never been whether there is somewhere worth going. The question is whether the universe will let us get there. And the answer begins with distance. Not distance as humans normally experience it. Not the kind that patience and fuel can overcome. A different kind entirely. A distance so extreme that it transforms every variable in the problem and makes the journey itself physically hostile to the traveler. This is where the first wall rises. Right now, the farthest human-made object in existence is a spacecraft roughly the size of a small car drifting through darkness beyond our solar system. Voyager 1 launched from Kennedy Space Center on September 5, 1977. Its original mission was to study Jupiter and Saturn up close. It completed that mission decades ago. Since its flyby of Saturn in November of 1980, Voyager 1 has been traveling on the same trajectory at the same speed. Heading outward into interstellar space, it crossed the boundary of the heliosphere, the protective bubble of charged particles generated by our Sun, in August of 2012. It became the first human-made object to enter interstellar space. It has been out there alone ever since. Now it is approaching another milestone. On November 18th, 2026, at roughly 2:16 in the morning Pacific time, Voyager 1 will become the first human-made object to reach one full light day from Earth. NASA confirmed this projection in its April 2026 Voyager status update. One light day means that a radio signal traveling at the speed of light, the fastest anything can move in this universe, will take 24 hours to reach the spacecraft. Send a command in the morning. Wait all day, wait all night. The response arrives the following morning, a full day for light itself to bridge the gap. Voyager 1 travels at approximately 17 kilometers per second. That is roughly 38,000 miles per hour. At that speed, you could circle the Earth in roughly 40 minutes. You could reach the Moon in about 6 hours. You could cross the distance from Earth to Mars at closest approach in fewer than 60 days. Voyager 1 is fast by any standard human beings have ever applied to a moving object, and it has been flying for nearly 50 years. In that time, it has covered roughly 1 light day. 1. That number needs to settle in your mind for a moment. Because the nearest star to our solar system, Proxima Centauri, is not 1 light day away. It is 4.24 light years away. A light year contains 365¼ light days. Proxima Centauri sits approximately 1,550 light days from Earth. Voyager 1, after half a century of uninterrupted flight, has crossed less than 1/1500th of the distance to the closest star. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would arrive in approximately 73,000 years. 73,000 years ago, modern humans shared the planet with Neanderthals. The entire history of agriculture, writing, cities, mathematics, empires, industry, and space exploration fits inside the last 10,000 years. Voyager would need 7 times that span to reach one star, the nearest one. And here is a detail that makes the distance even more disorienting. Voyager 1 has not actually left home. It crossed the heliosphere in 2012, passing beyond the bubble of charged particles streaming outward from the sun. That milestone was real and significant. But the sun's gravitational territory extends far beyond the heliosphere. Our star holds a vast shell of icy bodies in its gravitational grip, a structure called the Oort cloud. This enormous reservoir of comets and frozen debris is believed to begin at roughly 2,000 astronomical units from the sun and stretch outward to as far as 100,000 astronomical units, approximately 1.5 light years. It forms a diffuse spherical shell surrounding the entire solar system, marking the true gravitational boundary of our star's domain. Voyager 1, at 166 astronomical units, has not reached the inner edge of this shell. It will not enter the Oort cloud proper for centuries. It will not clear the outer boundary for roughly 30,000 years. And at that point, after 30,000 years of flight, Voyager will still not be halfway to Proxima Centauri. The heliosphere was never the border. It was a curtain inside a much larger room. Voyager has pushed through the curtain. The door is 30,000 years ahead. The nearest neighbor is 40,000 years beyond that. So let me try to make the distance tangible. Imagine shrinking the entire solar system so that the sun becomes a basketball sitting on a sidewalk in New York City. At this scale, Earth would be a small grain of sand orbiting roughly 26 meters away, about 85 feet. Jupiter would be a marble roughly 135 meters from the basketball, a block and a half down the street. Neptune, the outermost major planet, would be a small pea sitting roughly 800 meters away, about half a mile. The entire known solar system fits within a modest walk through a single burrow. Voyager 1, after nearly 50 years of flight, would have traveled roughly 40 blocks beyond Neptune at this scale. It would still be in Manhattan. Now find Proxima Centauri. At this same scale, the nearest star would be another basketball sitting on a sidewalk in Honolulu, Hawaii, over 4,000 miles from New York. Between those two basketballs stretches nothing. No gas stations, no landmarks, no waypoints, no emergency shelters. Just 4,000 miles of the bare emptiness with a few grains of sand clustered near one basketball and nothing at all until you reach the other. That is the interstellar void. And the void is not merely empty by human standards. It is empty beyond what laboratories on Earth can reproduce. the interstellar medium averages roughly 1 hydrogen atom per cubic centimeter. Compare that to the air you are breathing right now, which contains approximately 25 billion molecules per cubic centimeter. The best vacuum chambers ever built still contain millions of molecules per cubic centimeter. The space between stars puts them to shame. This is where a distinction must be drawn that most discussions of space travel skip past too quickly. Interplanetary travel and interstellar travel are not different points on the same spectrum. They are fundamentally different categories of problem. The distinction is not one of degree. It is one of kind. Consider what humanity has achieved within the solar system. We have landed rovers on Mars and driven them across its surface for years. We have dropped a probe onto Titan, the moon of Saturn, and photographed its methane lakes. We have sent spacecraft past every major planet, including a flyby of Pluto at the edge of the solar system. We have parked an observatory at the second Lagrange point, 1.5 million kilometers from Earth. These are genuine triumphs. But they all share one critical feature. They were accomplished within a region where distances are measured in light minutes or light hours. A signal from Earth to Mars takes between 4 and 24 minutes, depending on orbital positions. That delay is manageable. Errors can be corrected. Software can be uploaded. Trajectories can be adjusted. The spacecraft remains within communicative reach of the people who built it. The distance to Proxima Centauri is roughly 700,000 times the distance from Earth to Mars at closest approach. That is not a percentage increase. It is a multiplication by a factor approaching 1 million, nearly 6 orders of magnitude. It is the difference between walking across a room and walking across a continent. The tools that work at one scale do not function at the other. To appreciate how far current technology sits from closing this gap, consider the fastest spacecraft ever built, the Parker Solar Probe. Launched by NASA in 2018, holds the all-time speed record for a human-made object relative to the Sun. During its closest approaches to the solar surface, it reaches speeds exceeding 190 kilometers per second, roughly 430,000 miles per hour. That is fast enough to travel from New York to Los Angeles in about 20 seconds. Even at that velocity, a journey to Proxima Centauri would take approximately 6,700 years, longer than the entire span from the construction of the Great Pyramid to this moment. And the Parker Solar Probe only hits that speed during brief gravitational slingshots around the Sun. It cannot sustain it. No existing spacecraft can. The gap between what humanity can build today and what interstellar travel demands is not a gap that incremental improvement will close. Chemical rockets produce exhaust velocities of 3 to 5 kilometers per second. The most advanced ion engines tested in space achieve 30 to 50 kilometers per second. To reach even 1% of the speed of light, roughly 3,000 kilometers per second, would require propulsion technology that does not exist outside of theoretical papers. And at 1%, the speed of light? Proxima Centauri is still over 420 years away. Distance is the first barrier. It earns that title not because it is the tallest, but because it forces every other barrier into existence. It eliminates rescue and resupply. It severs communication. It demands that machines outlast empires and that human bodies endure what evolution never prepared them for. And it forces every potential traveler into a choice. Go slow or go fast. Both options look reasonable from a distance. Both collapse on closer inspection. The slow path beckons first. The logic seems almost elegant at first. If the problem is distance, and if speed is limited, then perhaps the answer is patience. Build a vessel large enough to carry a community. Stock it with everything a small civilization might need. Launch it toward the nearest star at whatever speed your engines can manage, and accept that the journey will take centuries. Let the passengers live their lives aboard the ship. Let their children carry the mission forward. Let grandchildren and great-grandchildren inherit the purpose until someday a generation that never saw Earth steps onto the surface of another world. This is the generation ship. It is the most frequently proposed solution to the interstellar distance problem, and it has captivated thinkers for nearly a century. Konstantin Tsiolkovsky described the concept in 1928, calling it a kind of Noah's Ark, equipped with engines and designed for journeys lasting thousands of years. Robert Heinlein explored it in fiction. Arthur C. Clarke refined it. Project Hyperion, run by the Initiative for Interstellar Studies, produced detailed engineering proposals for multi-generation crewed vessels. The idea keeps returning because it appears to sidestep the most obvious physical barriers. You do not need relativistic speeds. You do not need exotic propulsion. You do not need to break any law of physics. You just need a ship that lasts and a population that endures. But when you examine what lasting and enduring actually require across interstellar timescales, the generation ship does not sidestep the barriers at all. It trades the barriers of speed for the barriers of time. And time, given enough of it, destroys everything human beings have ever built. Start with what slow actually means in interstellar terms. Even ambitious propulsion concepts that do not yet exist cannot make slow travel fast. A nuclear pulse engine, the most powerful propulsion system ever seriously studied, was the basis of Project Orion in the 1950s and 60s. It proposed detonating nuclear bombs behind a massive pusher plate to accelerate a spacecraft. Theoretical performance estimates suggested speeds of 3 to 5%. The speed of light might be achievable with large enough vehicles. At 5% of light speed, the trip to Proxima Centauri takes roughly 85 years. That is within a single human lifetime, though barely, and only if everything goes perfectly. Few serious proposals achieve even this. More realistic nuclear thermal or nuclear electric systems, the kind NASA is currently developing for Mars missions, max out at speeds orders of magnitude below 1% of light speed. At those velocities, Proxima Centauri is thousands of years away. For any technology plausibly available in the coming century, interstellar transit times fall somewhere between several centuries and several tens of thousands of years. That means the generation ship does not need to work for a decade or a century. It needs to work for longer than most civilizations on Earth have lasted. And it needs to work perfectly, in total isolation, with no external help, in the most hostile environment human beings have ever encountered. The first thing that kills the crew is invisible, beyond the protective cocoon of Earth's magnetic field and atmosphere. Space is saturated with radiation. Two sources dominate. Solar particle events produce intense bursts of protons during solar flares and coronal mass ejections. These are dangerous but intermittent, and a spacecraft within a solar system can be designed to shelter its crew during events that last hours or days. The second source is far worse for long-duration travel. Galactic cosmic rays are high-energy particles, mostly protons, but including heavier nuclei like iron, that originate from sources outside the solar system. Supernova remnants, neutron stars, black hole environments. These particles travel at nearly the speed of light and carry enormous energy. A single galactic cosmic ray iron nucleus can pack more kinetic energy than a professionally pitched baseball, compressed into a particle smaller than an atom. Earth's magnetic field deflects most galactic cosmic rays. Its atmosphere absorbs much of what remains. Humans on the surface receive a background radiation dose of roughly 2 to 3 millisieverts per year from cosmic sources. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere, but at reduced shielding, receive roughly 150 to 200 millisieverts per year. Beyond the magnetosphere in interstellar space, the unshielded dose from galactic cosmic rays alone climbs to roughly 600 millisieverts per year or higher. 600 millisieverts per year means that within 5 to 10 years of unshielded exposure, every person aboard a generation ship would exceed the lifetime radiation dose limits NASA currently sets for astronauts. Cancer rates would climb. Cardiovascular disease would accelerate. Research from the NASA Space Radiation Laboratory at Brookhaven National Laboratory, where mice are exposed to simulated galactic cosmic ray fields, has demonstrated persistent damage to brain structure and cognitive function. Hippocampal neurogenesis, the process by which the brain forms new neurons, critical for learning and memory, declines significantly after exposure to heavy ion radiation at doses comparable to a multi-year deep space mission. The damage is not temporary. It persists for the life of the organism. Shielding can reduce the dose, but the physics of galactic cosmic ray interaction makes conventional shielding counterproductive beyond a certain thickness. When a high-energy heavy nucleus strikes a metal hull, it does not simply stop. It fragments, producing a shower of secondary particles, neutrons, protons, and lighter nuclei that can be more biologically damaging than the original particle. This is called spallation, and it means that adding more aluminum or steel to a ship's hull can actually increase the radiation dose to the crew rather than decrease it. Effective shielding requires hydrogen-rich materials, water, polyethylene, or dedicated liquid hydrogen tanks layered thick enough to slow and absorb both primary particles and secondary showers. The mass penalty is severe. Estimates for adequate galactic cosmic ray shielding on a crewed interstellar vessel range from several meters of water-equivalent material surrounding the entire habitable volume. For a ship large enough to house hundreds of people, this means thousands or tens of thousands of additional tons of shielding mass, all of which must be accelerated to cruising speed alongside everything else the ship carries. Every kilogram of shielding is a kilogram that could have been food, fuel, or equipment. And even with shielding, the dose is reduced, not eliminated. Over centuries of travel, cumulative exposure accumulates generation after generation. Genetic damage passes to offspring. Mutations build in the population's gene pool. A ship that launches with a healthy crew arrives with a population carrying centuries of radiation-induced genetic burden. No ground-based experiment has ever modeled what this looks like across 10 or 20 human generations, because no experiment has ever needed to. The second biological crisis is genetic diversity. A generation ship cannot carry millions of people. Propulsion limits, life support capacity, and structural constraints restrict the founding population to hundreds or at most a few thousand individuals. Population genetics studies suggest that a minimum viable population for long-term survival without unacceptable inbreeding sits somewhere between 500 and 5,000 people. Depending on assumptions about reproductive management and genetic screening, below this threshold, genetic diversity erodes with each generation. Recessive deleterious mutations become more likely to pair. Inbreeding depression manifests as reduced fertility, increased susceptibility to disease, and developmental abnormalities. Managing genetics across centuries of travel requires active intervention. Reproductive pairing must be guided or constrained to maximize outbreeding. Stored genetic material, sperm banks, egg banks, perhaps frozen embryos, must remain viable for the entire journey. Cryopreservation technology works on timescales of decades, not centuries. No biological sample has ever been preserved in a functional state for 300 years, and any system of managed reproduction raises ethical questions so profound that no human society has ever attempted to implement one at this scale. Who decides which individuals may reproduce with whom? By what criteria? Who enforces compliance aboard a vessel where the subjects cannot leave? The third biological crisis receives less attention, but may be equally destructive. The human body was not designed for weightlessness. It was sculpted by 4 billion years of evolution under 1 g of gravitational pull. When that pull disappears, the body begins to dismantle itself. Data from the International Space Station reveals a consistent pattern. Bone density decreases at a rate of roughly 1 to 2% per month in load-bearing bones. Muscles atrophy despite daily exercise of 2 hours or more. The cardiovascular system weakens and remodels. The heart changes shape, becoming more spherical. Fluid redistributes toward the head, increasing intracranial pressure, affecting the optic nerve and deforming the eyeball. NASA has classified this condition, spaceflight-associated neuroocular syndrome, as one of the top health risks for long-duration missions. Some astronauts return from year-long stays with permanent changes to their vision. On the station, gravity reverses most damage upon return to Earth. A generation ship offers no return. The crew lives in microgravity or reduced gravity for their entire lives. Their children are born into it. Over generations, cumulative skeletal and muscular deterioration would produce a population physically incapable of functioning on a planetary surface. Artificial gravity through rotation is real physics, and it works. But the human vestibular system is sensitive to rotational motion. If the habitat spins too quickly, occupants experience severe motion sickness from Coriolis effects. Studies suggest rotation rates above roughly 2 revolutions per minute produce unacceptable discomfort. To stay below this threshold while generating 1G, the habitat must have a radius of at least 225 meters, a spinning structure roughly 450 meters across. The mass is enormous. The bearings connecting rotating and non-rotating sections must function without maintenance for the entire voyage. And there are unknowns that no experiment has ever addressed. What happens to embryonic development at 1/3 G over multiple generations? Whether bone formation in children fails below some gravitational threshold that has never been measured. Because there has never been a reason to measure it. The generation ship must choose a gravity level and commit to it for the entire voyage, with no ability to correct the decision if the chosen level turns out to damage the biology of every person born aboard. But even if radiation could be fully shielded, genetics carefully managed, and gravity somehow solved, the ship must still sustain its passengers biologically for the entire journey. That means food, water, and air recycled without loss for centuries. And that is where the next wall rises. No closed ecological life support system has ever operated successfully for more than a few years. Biosphere 2, built in Arizona in the late 1980s, was the most ambitious attempt, a sealed enclosure of roughly 3.14 acres. It housed 8 people and was designed to recycle all air, water, and food indefinitely using a miniature ecosystem of plants, animals, insects, and microbes. It failed within the first 2 years. Oxygen levels dropped dangerously as carbon dioxide accumulated beyond what the plants could process. Concrete inside the structure absorbed oxygen through chemical reactions no one had anticipated. Insect populations crashed. Pollination failed. Crop yields collapsed. The crew experienced chronic hunger and escalating interpersonal conflict. Biosphere 2 had to be opened and resupplied. The Soviet Bios 3 experiment in the 1970s achieved longer closure durations, up to 180 days, with a simpler system based on algae cultivation and wheat farming in a much smaller habitat. It provided lessons about gas exchange and waste recycling, but never approached the complexity or duration required for interstellar travel. The European Space Agency's EMELISA project has been studying closed-loop life support for decades and has made progress on individual subsystems, waste processing, air revitalization, water recovery, but it has not yet demonstrated a fully closed system capable of sustaining even a small crew indefinitely. The International Space Station does not even attempt closure. It receives regular resupply missions carrying food, water, oxygen, spare parts, and equipment. Its life support systems recycle some water and scrub carbon dioxide from the air, but it depends utterly on Earth for survival. Without resupply, the station would become uninhabitable within months. A generation ship must achieve what no habitat in human history has achieved: total closure, complete recycling, zero external input, for 300 years, or 3,000 years, or 30,000 years. Every atom of carbon, every molecule of water, every trace element required for biology must cycle endlessly without accumulating in the wrong reservoir or leaking into unusable forms. In Earth's biosphere, these cycles are maintained by a planet-sized system with oceans, forests, atmospheric circulation, tectonic activity, and 4 billion years of evolutionary tuning. Replicating this inside a metal hull is not an engineering challenge in the conventional sense. It is an attempt to build a miniature planet from scratch and keep it running longer than any human structure has ever survived. Which brings us to the next wall. Machines break. Everything breaks. And nothing humans have ever built keeps running for centuries without repair. Voyager 1 is the longest operating spacecraft in history. Launched in 1977, it has been functioning in some capacity for nearly 50 years. But functioning is a generous description. Most of its scientific instruments have been shut down to conserve dwindling power from its radioisotope thermoelectric generators. Those generators produce electricity from the decay of plutonium-238, and they lose roughly 4 watts of output per year. By 2026, Voyager 1's power budget has dropped to roughly 225 watts, barely enough to run a few light bulbs. Within the next few years, there will not be enough power to operate anything at all. Voyager 1 will go silent, not because it was destroyed, because its power source decayed on schedule. The specific dependencies of the International Space Station reveal how deep the mechanical problem runs. Its oxygen generation system requires chemical canisters manufactured on the ground. Its water recycling system uses filters that wear out and must be replaced with Earth-built components. Its attitude control system depends on thrusters consuming fuel delivered from the surface. Every critical function aboard the station traces back to a supply chain that begins on Earth, on the ground. Complex machines survive through the same principle. A jet engine lasts tens of thousands of flight hours because worn turbine blades are replaced with new ones manufactured in factories that source materials from mines that extract ore from the ground. Every link in that chain depends on an industrial civilization with millions of workers, global logistics, and raw material extraction. A generation ship has none of this. It carries whatever it launched with. If a critical pump fails in year 200 and no replacement exists aboard, the system it served stops working permanently. If that system was part of the life support loop, people start dying. A ship could theoretically carry workshops, fabrication equipment, and raw material stockpiles sufficient to manufacture replacement parts on board. But this adds enormous mass, enormous complexity, and the need for skilled technicians across every generation. Training programs must function continuously for centuries. Knowledge must transfer perfectly from one generation to the next. A single generation that fails to train enough machinists, enough chemists, enough electrical engineers risks a cascading loss of maintenance capability from which the ship cannot recover. This is where the mechanical barrier meets the civilizational barrier. Because machines require people to maintain them, and people require functioning social structures to maintain specialized knowledge. Long-duration isolation studies on Earth provide grim precedents. The Mars 500 experiment conducted in Moscow between 2010 and 2011 confined 6 volunteers in a sealed habitat for 520 days to simulate a Mars mission. The crew experienced sleep disruption, depression, social withdrawal, and interpersonal conflict. one crew member became so sedentary and disengaged that researchers worried about his physical and psychological health. And these were carefully selected, highly motivated volunteers who knew the experiment would end, who could communicate with the outside world, and who were confined for fewer than 2 years. A generation ship confines its population not for months or years, but for lifetimes. Children born aboard the ship never chose the mission. They inherit it. They grow up inside a metal hull with no horizon, no weather, no natural landscape, no possibility of leaving. They know from the moment they are old enough to understand that they will live and die inside this container, and that the destination their great-great-grandparents chose will not be reached in their lifetimes. What does this do to motivation? What does it do to the willingness to maintain complex technical systems that serve a goal you will never personally see fulfilled? Historical precedents are not encouraging. After the fall of the Western Roman Empire in the 5th century, Europe lost the ability to produce concrete. Roman concrete, a material so durable that structures built with it still stand 2,000 years later, required specific knowledge of volcanic ash ratios, mixing techniques, and curing processes. That knowledge vanished within a few generations. It was not rediscovered until the 18th century, over 1,000 years later. The Romans also built aqueduct systems of extraordinary precision, engineered to maintain a steady gradient across miles of terrain. After the empire collapsed, the maintenance knowledge disappeared. Cities that had enjoyed running water for centuries reverted to wells and rain collection. The technology was visible. The structures were standing. The knowledge to keep them functioning was gone. The Polynesian navigation traditions offer an even more pointed example. For thousands of years, Pacific Islanders crossed vast stretches of open ocean using a system based on star positions, wave patterns, bird behavior, and subtle changes in water color and temperature. This knowledge was transmitted orally from master navigators to apprentices across dozens of generations. It worked flawlessly. Then European contact disrupted the transmission chain. Within 3 generations, much of the knowledge was nearly lost. A system that had survived thousands of years of transmission collapsed in fewer than 100 when the social structures supporting it were disrupted. The United States Department of Energy has spent decades attempting to design warning markers for nuclear waste repositories that must remain comprehensible for 10,000 years. The problem is not engineering. The markers can be made durable. The problem is language. No human language has survived unchanged for 10,000 years. No symbol system has maintained consistent meaning across that span. Panels of linguists, anthropologists, and semioticians reached a humbling consensus. There is no known method for guaranteeing that a message created today will be understood by humans 10,000 years from now. A generation ship needs its crew to transmit not a simple warning, but an entire technical civilization across centuries of isolation, metallurgy, chemistry, medicine, electrical engineering, software development, agricultural science, mechanical repair, dozens of specialized disciplines, each requiring years of training, each depending on the others. If any single generation fails to produce enough trained specialists in any single critical field, the ship loses the ability to maintain the systems that depend on that field. And unlike Earth, where lost technology can sometimes be rediscovered through experimentation or contact with other cultures, a generation ship has no external source of knowledge. What is lost stays lost. The library is finite. The teachers are mortal. And the students may not want to learn what their parents insist they must. There is a final trap the generation ship cannot escape. The entire concept depends on knowing before launch that a habitable world exists at the end of the journey. This knowledge comes from telescopes. Astronomers detect a planet in the habitable zone, analyze the spectrum of its atmosphere, and infer conditions that might support life. But inference is not confirmation. A spectrum tells you which molecules float in an atmosphere, It does not tell you whether the surface is solid or molten, whether the oceans are acidic, whether the soil is toxic, or whether microbiology lethal to Earth organisms waits on the ground. Many promising habitable zone exoplanets orbit red dwarf stars, prone to violent flares that could strip a planet's atmosphere entirely. The telescopic data says a planet might be habitable. It cannot say a planet is habitable. That determination requires being there. And the history of planetary science is a history of expectations overturned. Before spacecraft visited Venus, many scientists expected a warm, wet world. The reality was a surface hot enough to melt lead under crushing carbon dioxide. Before rovers landed on Mars, some models predicted accessible subsurface water. The reality has proven far more hostile. A generation ship cannot hedge this bet. It carries no fuel for a second destination. It cannot turn around. If the planet turns out to be uninhabitable, centuries of survival, of radiation endured, of machines maintained, of generations born and buried in transit, end not in triumph, but in extinction at the finish line. And here's the paradox that closes the slow travel trap. Every problem the generation ship faces gets worse the longer the journey takes. Radiation accumulates, ecosystems drift, machines wear, societies strain, knowledge degrades. Slowing down does not reduce risk. It increases every risk simultaneously. The slow path does not solve the distance problem. It repackages it into the barriers of biology, mechanics, psychology, and civilization. And so the mind turns naturally to the alternative. If slow travel collapses under the weight of time, then the obvious answer is to go faster, compress the journey, accelerate to a significant fraction of the speed of light, and cross the gulf before biology, machinery, and sanity give out. Speed conquers time. But speed has a cost, and the cost is not measured in fuel alone. In everyday life, doubling the speed of a moving object quadruples its kinetic energy. A car traveling at 60 miles per hour carries 4 times the energy of the same car at 30. This is classical physics, the simple relationship taught in introductory courses. It holds beautifully for baseballs, automobiles, and even spacecraft at the modest speeds humanity currently achieves. It stops holding as you approach the speed of light. Special relativity, confirmed by over a century of experimental evidence, describes what actually happens to energy at extreme velocities. As an object accelerates toward the speed of light, its effective mass increases, not its rest mass, not the number of atoms it contains, but the amount of energy required to push it even slightly faster. The closer you get to light speed, the more energy each additional increment of velocity demands. At 90% of light speed, the energy required to accelerate the object further has already grown to more than double what classical physics would predict. At 99%, the energy requirement climbs by a factor of roughly 7. At 99.9%, the factor exceeds 22. The relationship is not linear. It is not even polynomial. It curves upward toward infinity as velocity approaches light speed, and it never levels off. What does this mean in practical terms? Consider a spacecraft with a total mass of 10,000 kilograms, roughly the mass of a large truck. At 10% the speed of light. This vehicle carries a kinetic energy of approximately 4.5 times 10 to the 18th power joules. That is roughly 1,000 megatons of TNT, the largest nuclear device ever detonated. The Soviet Tsar Bomba yielded approximately 50 megatons. To accelerate a single truck-sized spacecraft to 10% of light speed requires roughly 20 times the energy of the most powerful nuclear explosion in human history. And a truck is not a crewed starship, a crewed interstellar vessel with life support, shielding, fuel, and habitat would mass hundreds of thousands of kilograms at minimum. Scale the energy accordingly, and the numbers enter a realm that no longer belongs on engineering spreadsheets. They belong in astrophysics, in the energy budgets of stars and supernova. And 10% of light speed is modest by interstellar standards. At that velocity, Proxima Centauri is still over 42 years away. If you want a trip time measured in single-digit years, you need to push significantly faster. At 50% of light speed, the energy requirement for a 100,000 kilogram crude vessel climbs to roughly 1.4 times 10 to the 21st power joules. At 90%, it reaches approximately 1.2 times 10 to the 22nd power joules. To put these numbers in perspective, total global energy consumption by all of human civilization in the year 2024 was approximately 5.8 times 10 to the 20th power joules. That means accelerating a modestly sized crude vessel to 50% of light speed requires roughly 2.5 years of total energy output from every power plant, every engine, every furnace, and every battery on Earth. Combined. To reach 90%, you would need over 20 years of total global energy production poured into a single vehicle. And these figures assume perfect conversion of energy into kinetic motion with zero waste, which is physically impossible. This is the energy wall. It does not depend on what propulsion system you use. It does not depend on engineering cleverness or future breakthroughs. It is a consequence of the relationship between mass, velocity, and energy as described by special relativity, which has been confirmed by every particle accelerator experiment ever conducted. No amount of technological progress changes the amount of energy required to accelerate a given mass to a given speed. Technology can change how efficiently you convert fuel into thrust. It cannot change how much energy the universe demands for a particular velocity. And the energy wall is only the entrance fee. You have not yet built the rocket. In 1897, the Russian physicist Konstantin Tsiolkovsky derived an equation that would haunt every propulsion engineer who followed him. The Tsiolkovsky rocket equation describes the relationship between a rocket's exhaust velocity, the ratio of its fueled mass to its empty mass, and the maximum change in velocity it can achieve. The equation is elegant. Its implications are brutal. A rocket carries its own fuel. As it burns fuel and ejects exhaust to produce thrust, it gets lighter. The lighter it gets, the more efficiently it accelerates. This sounds like a virtuous cycle, but the equation reveals that the mass of fuel required grows exponentially with the desired speed. Not linearly, not as a square. Exponentially. Doubling the desired velocity does not double the fuel requirement. It roughly squares it. Tripling the velocity roughly cubes it. Reaching interstellar speeds requires mass ratios so extreme that the numbers leave physical reality behind. For conventional chemical rockets, the exhaust velocity is roughly 3 to 5 kilometers per second. To reach even 1% of the speed of light, approximately 3,000 kilometers per second, using chemical propulsion, the mass ratio required would be so large that the amount of fuel exceeds the mass of the observable universe by many orders of magnitude. This is not an exaggeration. It is a direct calculation from the Tsiolkovsky equation. Chemical rockets cannot reach interstellar speeds. The mathematics forbids it absolutely. Nuclear thermal rockets improve the exhaust velocity to roughly 8 to 9 kilometers per second. The mass ratio drops, but remains absurdly high. Ion engines push exhaust velocities to 30 to 50 kilometers per second. Better. Still nowhere near sufficient. Theoretical fusion rockets might achieve exhaust velocities of several hundred to, perhaps, 700 kilometers per second. This brings the mass ratio into a range where interstellar travel becomes mathematically conceivable. But the rocket equation still punishes the attempt ruthlessly. At the optimistic end, a 150-ton spacecraft trying to reach 8% of light speed would require a mass ratio so extreme that the initial fuel load would outweigh the payload by a factor of nearly 10 to the 15th power. A quadrillion kilograms of fuel for every kilogram of ship. At lower fusion exhaust velocities, the number climbs further, rapidly reaching masses that dwarf entire planetary systems. Only one theoretical fuel source breaks the rocket equation's tyranny: antimatter. When a particle of matter meets its antiparticle, both annihilate completely, converting nearly 100% of their combined mass into energy. This is roughly 3 orders of magnitude more efficient than nuclear fusion, and roughly 10 orders of magnitude more efficient than chemical combustion. An antimatter-powered rocket could, in principle, achieve mass ratios that make interstellar velocities reachable with a reasonably sized spacecraft. But antimatter exists only in theory, as a fuel. In practice, the total amount of antimatter ever produced by humanity across every particle accelerator on Earth over several decades amounts to less than 10 nanograms. CERN, the only facility with a dedicated antimatter production program, reported in 2025 that its latest techniques allow the production of roughly 15,000 antihydrogen atoms in a matter of hours, a breakthrough that its own researchers called science fiction. Just 10 years earlier, 15,000 atoms weigh roughly 2.5 times 10 to the negative 21st power grams. To fuel even a modest interstellar spacecraft would require grams or kilograms of antimatter. The gap between current production and mission requirements spans more than 20 orders of magnitude. It is the difference between a single raindrop and all the water in the Pacific Ocean. Furthermore, antimatter annihilates on contact with any ordinary matter, meaning it must be suspended in perfect vacuum using electromagnetic fields. No storage system capable of holding macroscopic quantities for the duration of a mission has ever been built or even convincingly designed, and the energy required to manufacture antimatter exceeds the energy the antimatter itself contains by a factor of roughly 10 billion. You spend 10 billion joules to produce 1 joule's worth of antimatter fuel. The process does not store energy, it destroys it. Antimatter propulsion is not an engineering problem awaiting a clever solution. It is a resource problem of a kind humanity has never faced, requiring a substance that does not naturally exist in our part of the universe, produced by processes that consume far more energy than they yield, stored by methods that do not yet work. So the energy wall stands, reinforced by the rocket equation. No existing or near-future propulsion system can accelerate a crewed spacecraft to interstellar velocities without requiring either impossible quantities of fuel or an energy source that humanity cannot produce in usable amounts. The physics is clear. The mathematics is settled. The barrier is not a lack of imagination. It is the relationship between mass, energy, and velocity as the universe has defined it. But suppose, for the sake of exploration, that some future civilization solves the energy problem entirely. Suppose they build a fusion reactor of unimaginable power, or learn to manufacture antimatter in bulk, or develop some entirely novel propulsion system that current physics cannot predict. Suppose they accelerate a crewed vessel to 10 or 20% of the speed of light and send it hurtling toward another star. They have cleared the energy wall. They have beaten the rocket equation. And they have just transformed the interstellar medium from an empty void into a hailstorm of destruction. Because the universe does not need to place obstacles between the stars. It only needs to scatter a few atoms per cubic centimeter across the void. Speed does the rest. A single interstellar dust grain with a mass of 1 milligram, smaller than a grain of sand, smaller even than the width of a human hair, carries a kinetic energy of approximately 450 million joules when it strikes a surface moving at 10% of light speed. For context, a bullet fired from a .357 Magnum handgun delivers roughly 720 joules of energy on impact. The dust grain strikes with the force of over 600,000 bullets arriving simultaneously at a single point. That is not a collision. It is a detonation. The grain and the surface it strikes vaporize instantly. A crater forms. Molten material sprays outward. The impact is equivalent to a small bomb detonating against the hull. Research conducted at Lawrence Livermore National Laboratory modeling the effects of interstellar dust on relativistic spacecraft calculated that over a 4-light-year journey at 20% of light speed, cumulative dust impacts could erode, melt, or vaporize more than 0.5 millimeter of a quartz surface across the entire forward-facing area of the vehicle. More recent modeling published in the Astrophysical Journal examined the interaction of relativistic spacecraft with the interstellar medium in finer detail. The results confirmed that even for gram-scale probes, dust grain impacts at 20% of light speed modify material structure through melting, and gas atom bombardment heats the leading surface to significant equilibrium temperatures. At 50% of light speed, the energy of each grain impact scales by roughly an order of magnitude. At that velocity, a 1 milligram grain delivers energy comparable to a large conventional bomb, and grains are not the only hazard. The interstellar medium also contains ice fragments, micropebbles, and debris of unknown composition and size distribution between micron-sized dust and small asteroids. The size spectrum of material in interstellar space is poorly characterized because detecting objects smaller than a star from light years away is functionally impossible. A ship traveling at half the speed of light for a decade sweeps out a volume large enough that encountering an object far more massive than a dust grain becomes statistically plausible. A single impact from a pebble-sized object at that velocity would release energy equivalent to a nuclear weapon. Shielding against these impacts is theoretically possible, but practically devastating. A forward-mounted sacrificial shield, a massive plate of expendable material positioned ahead of the ship, could absorb impacts as it erodes over the journey, but the shield must be enormously thick to withstand billions of hydrogen atom impacts and thousands of dust grain strikes. Its mass adds directly to the fuel budget, which is already strained to breaking by the energy wall. Every kilogram of shielding requires additional fuel to accelerate, which requires additional fuel to accelerate the fuel, which spirals upward through the exponential cruelty of the rocket equation. An electromagnetic deflector, a powerful magnetic field projected ahead of the ship, works in principle for charged particles, but fails for neutral atoms, neutral dust grains, and any macroscopic debris. It also requires enormous power to maintain, competing directly with propulsion. But dust is not the worst of what speed does. The hydrogen atoms themselves become weapons. At rest, a hydrogen atom in interstellar space is harmless. It drifts invisibly, carrying negligible energy. But in the reference frame of a spacecraft moving at a significant fraction of light speed, every hydrogen atom in the path ahead approaches at that same fraction of light speed, at 10% of light speed. Each hydrogen atom strikes the hull with an energy of roughly 5 megaelectronvolts, comparable to the energy of particles used in medical radiation therapy. At 50%, the energy per atom climbs to nearly 150 megaelectronvolts. At 90%, it enters the giga-electron-volt range, comparable to particles in high-energy accelerator experiments. The forward-facing surface of the ship experiences a continuous bombardment of hydrogen and helium nuclei at energies equivalent to a particle accelerator beam aimed directly at the hull. This bombardment is not produced by some distant source. It is generated by the ship's own motion. The faster the ship travels, the more energetic the bombardment becomes. The ship is creating its own radiation storm by moving through a medium that would be completely harmless if the ship were stationary. At 50% of light speed, the forward-directed radiation flux would deliver lethal doses to an unshielded crew in a matter of days. The ship's speed, the very thing that was supposed to save the crew from the slow travel problem of cumulative radiation exposure, becomes itself the dominant source of radiation. The vacuum becomes a weapon. The universe does not need to place obstacles between the stars. It only needs to scatter a few atoms across the void. Speed does the rest. There is another constraint that connects the energy wall to the human body: acceleration tolerance. The human body can survive brief bursts of extreme acceleration. Fighter pilots endure 7 to 9 G during aggressive maneuvers with specialized pressure suits and training. They sustain those forces for only seconds. Sustained acceleration is a different matter. At 1 G, a person feels exactly as heavy as they feel standing on the ground, comfortable and indefinitely survivable. At 2 G, a 70-kilogram person feels as though they weigh 140 kilograms. Every movement becomes exhausting. Sleep becomes difficult. At 3 G and above, prolonged exposure causes tissue damage, impaired circulation, and eventually organ failure. Sustained acceleration above 1 G for a crewed vessel is not a design choice. It is a medical impossibility. At 1 G of sustained acceleration, it takes approximately 35 days to reach 10% of the speed of light, roughly 200 days, nearly 7 months, to reach 50%, approximately 1 year, to reach 77%. These are not negotiable. During the entire acceleration phase, the ship's engines must fire continuously. Every second of thrust consumes fuel. Every kilogram of fuel consumed was itself accelerated during the preceding seconds, meaning it already consumed fuel to get up to speed. The Tsiolkovsky equation penalizes long burn times with exponential fuel costs. Lowering the acceleration to reduce crew strain extends the burn and increases fuel consumption. Raising the acceleration to save fuel injures the crew. There is no favorable trade in either direction. The human body sets a ceiling. The rocket equation penalizes the long burns that ceiling requires. The two constraints squeeze the mission from opposite sides. And the acceleration phase is only the first half. The ship must stop. Accelerating to interstellar speeds consumes monstrous quantities of energy. Decelerating from those speeds consumes exactly the same amount. A ship that cannot decelerate does not arrive. It performs a flyby, screaming past the target star system with only minutes to collect data before the destination falls behind forever. For a crewed mission, the crew must slow down, enter orbit, and establish some presence at the destination. That means carrying enough fuel or energy to reverse the entire velocity. The deceleration problem effectively doubles the total energy requirement. If accelerating to 10% of light speed requires the energy equivalent of a year's global output, decelerating requires another year's worth. The fuel budget doubles. The mass doubles. The fuel needed to carry the extra fuel doubles again. The rocket equation's exponential penalty applies to both halves independently, meaning the combined mass ratio is roughly the square of the mass ratio for acceleration alone. Proposals for magnetic sails using the interstellar medium as a braking mechanism require superconducting coils spanning kilometers in diameter that must function after decades of relativistic radiation bombardment. Light pressure from the destination star could slow a light sail, but only for probes too light to carry a crew. For crewed vessels, the deceleration problem remains unsolved. And behind all of these barriers stands the absolute wall. The speed of light is not a speed limit in the way that highway speed limits are speed limits. It is a structural feature of space-time itself. As a massive object approaches the speed of light, the energy required approaches infinity. Not a very large number. Infinity. This has been confirmed by every particle accelerator in history. CERN's Large Hadron Collider accelerates protons to more than 99.9999% of light speed. Each proton carries the kinetic energy of a flying mosquito, not because it is massive, but because its effective energy has grown by a factor of roughly 7,000 beyond its rest mass energy. Reaching 100% would require infinite energy. This is observed fact, measured in laboratories every single day. Time dilation is often presented as a gift that relativity offers to interstellar travelers. At 90% of light speed, the crew experiences time at roughly 44% of the normal rate. At 99%, 1 year aboard equals roughly 7 on Earth. But consider a crewed mission to a star 40 light-years away at 95% of light speed. The journey takes roughly 42 years each way by Earth's calendar, but only 13 years aboard. The crew departs in 2200. They return around 2285. 85 years have passed on Earth, 27 years for the crew. Everyone who launched the mission is dead. The civilization that designed it has transformed beyond recognition. The crew returns as strangers to a world that moved on without them, temporal exiles, drifting through the universe at a rate that no longer matches the species they belong to. And time dilation only becomes significant at velocities where every other barrier is at its most severe. Below 50% of light speed, the dilation factor is barely 13%. The compression that matters requires speeds above 90%. Where dust detonates, hydrogen becomes a radiation storm, energy demands exceed civilizational output, and deceleration doubles every cost. Time dilation is not a loophole. It is a feature that unlocks only at speeds where the chain pulls tightest. Two paths, two failure modes, they are not independent. They are the two ends of a single spectrum, connected by the distance between stars and governed by the same physical laws. Approach slowly and time devours you. Approach quickly and physics devours you. Add shielding and mass increases. Increase speed and radiation intensifies. Carry deceleration fuel and the mass that must be accelerated doubles. Build a larger ship and the energy requirement climbs further toward the impossible. Every solution is a cost. Every cost is a new barrier. Every barrier links back to the others in a closed loop of escalating demands. There is no free variable. There is no parameter that can be adjusted without tightening a constraint somewhere else. The physics does not offer a path through. It offers a chain, and every link is welded to the next. Perhaps the picture seems too abstract. Perhaps the barriers feel like problems that future technology will simply dissolve the way electricity dissolved the problem of darkness, or antibiotics dissolved the problem of infection. So let us walk through the most serious proposals that engineers and physicists have put forward for crossing interstellar space. Not to dismiss them, but to see clearly what each one actually solves and what it leaves standing. Fusion propulsion is the nearest term serious candidate. Nuclear fusion, the process that powers the sun, converts hydrogen into helium and releases energy far more efficiently than chemical combustion or nuclear fission. A fusion rocket would heat propellant to extraordinary temperatures and expel it at exhaust velocities of several hundred kilometers per second, perhaps approaching 700 in optimistic designs. This is roughly 100 times better than the best chemical rockets. It brings the rocket equation into a range where interstellar velocities are at least mathematically reachable. But reachable does not mean practical. Even with fusion exhaust velocities, a crewed spacecraft of a few hundred tons would require fuel masses equivalent to thousands or tens of thousands of times the payload mass to reach even a few percent of light speed. And a few percent of light speed means a journey to Proxima Centauri lasting a century or more. Every generation ship failure mode returns in full force. Radiation, ecosystem collapse, mechanical degradation, social fragmentation. Fusion shortens the journey from tens of thousands of years to hundreds. It does not shorten it to a human lifetime. The slow travel trap remains open, merely compressed. Furthermore, no fusion reactor on Earth has yet achieved sustained net energy gain, let alone been miniaturized into a spacecraft engine capable of continuous thrust for years. Fusion is real physics. fusion propulsion is still an aspiration. The Bussard ramjet was proposed in 1960 as a way to circumvent the fuel problem entirely. Instead of carrying fuel from launch, the ramjet would scoop hydrogen from the interstellar medium using an enormous magnetic funnel, compress it, and feed it into an onboard fusion reactor. The ship would accelerate continuously, gathering fuel as it traveled, never running out. The concept is elegant. The physics is devastating. The interstellar medium is so thin that collecting enough hydrogen for meaningful thrust would require a magnetic scoop spanning hundreds or thousands of kilometers in diameter. The energy required to maintain such a field is enormous, and the drag produced by interacting with the interstellar medium at high speeds may actually exceed the thrust the collected hydrogen can provide. Multiple analyses have concluded that the Bussard ramjet as originally conceived would function as a brake rather than an engine at velocities above a few percent of light speed. The medium you are scooping for fuel is the same medium that creates lethal dust impacts and radiation at those velocities. The fuel source and the hazard are the same substance. Antimatter propulsion remains the only theoretical fuel source with sufficient energy density to power a crewed interstellar mission at velocities high enough to avoid the slow travel trap. The barrier is not theoretical, but practical. Total antimatter production in human history amounts to less than 10 nanograms. The gap between that and mission requirements spans more than 20 orders of magnitude. The energy required to manufacture antimatter exceeds the energy it contains by a factor of roughly 10 billion. Storage methods that could hold macroscopic quantities do not exist. Antimatter propulsion is not an engineering problem awaiting a clever solution. It is a resource problem requiring a substance that does not naturally exist in usable quantities anywhere in our part of the universe. Laser sails offer a different approach entirely. Rather than carrying fuel, a spacecraft could be propelled by a beam of light from a powerful laser array. The Breakthrough Starshot initiative, announced in 2016 with $100 million in backing and Stephen Hawking's public endorsement, proposed using a ground-based laser array of 100 gigawatts to accelerate gram-scale probes to 20% of the speed of light. At that speed, a tiny probe could reach Alpha Centauri in roughly 20 years and transmit data back 4 years later. The concept addressed several barriers simultaneously. No fuel aboard, no rocket equation, no slow travel timeline. But the laser array would need to produce 100 gigawatts of coherent focused power, roughly equal to the entire output of every nuclear power plant in the United States combined. Directed with precision of fractions of an arcsecond onto a sail 4 meters wide, accelerating away from Earth at 40,000 times the force of gravity. By 2025, the project was effectively dormant. A Scientific American investigation revealed that only $4.5 million of the pledged $100 million had been spent. Meetings had ceased, funding had dried up, researchers had moved on, and even if Breakthrough Starshot had succeeded perfectly, it would have accomplished something narrow and specific. A flyby by a chip-sized probe carrying a camera. No humans, no deceleration, no orbit, no landing, no return. A postcard from the stars. Each proposal solves some links. None solves all of them. Fusion addresses propulsion, but not speed. Antimatter addresses speed, but not production. Laser sails address the energy source, but not the crew. Generation ships address the crew, but not time. Each concept breaks one section of the chain only to find that the remaining sections still hold. The barriers are not independent problems waiting for independent solutions. They are coupled. They reinforce each other. Solving one redistributes the load across the others. The total load does not decrease. This is the point where the framing itself must change. Because the chain does not break. It will not break for crewed interstellar travel within any time scale that maps onto human civilization as we understand it. Not because of one overwhelming obstacle, not because of a dramatic prohibition written into the laws of physics, but because of a system of constraints, each one rooted in fundamental physics, each one reinforced by the others, collectively producing a barrier that no single technology can overcome because the barrier is not singular. It is systemic. But physics does not forbid objects from entering interstellar space. Voyager 1 and Voyager 2 are there right now. Tiny robotic probes may follow within decades. These missions are physically possible. What the barriers prevent is not exploration. It is habitation. It is the transfer of living human beings from one stellar system to another, alive, functional, and capable of doing something meaningful upon arrival. That specific goal runs into the full weight of the chain. And this is where the question must shift. Not how do we send bodies to the stars, but how do we send presence? Strip the human body from the spacecraft and the chain loosens. Not one link, many links simultaneously. A robotic probe carrying advanced artificial intelligence needs no life support, no food, no water, no air recycling, no radiation shielding for biological tissue, no artificial gravity, no genetic diversity management, no social structure, no psychological endurance, no generational knowledge transfer. The mass drops by orders of magnitude. The energy requirement drops with it. The speed becomes achievable. The timescale shrinks. The interstellar medium remains hostile, but the probe can be hardened against it in ways a human body cannot. Barriers that were absolute for crude vessels become engineering challenges for machines. Difficult, but no longer forbidden by physics. Go further. Consider that the essence of human presence is not flesh, but information. DNA is a code. It can be digitized, stored as data, transmitted at the speed of light as a radio signal or a laser pulse, sent across 4 light years in 4 years and 3 months. No ship required, no fuel, no shielding, no deceleration. The information arrives intact because information does not suffer from radiation. It does not starve. It does not mutiny. It does not forget. A robotic system at the destination, delivered decades earlier by a hardened probe, could in principle receive that information, could in some future, far beyond current capability, use it to reconstruct biological organisms from raw materials available at the destination. Not carrying bodies across the void, carrying blueprints, sending the design, not the product. This is not a solution. It is a redefinition. Human beings do not reach the stars by traveling to them. They reach the stars by sending intelligence first, then blueprints, then building presence from the far end. If that does not sound like the interstellar travel you imagined, then perhaps it is the imagination that needs updating, not the physics. The chain holds for bodies. It may not hold for information. The universe built its barrier against mass, against biology, against the specific vulnerabilities of organisms that evolved on a single world under a single star. It did not build its barrier against data. It did not build its barrier against knowledge encoded in signals traveling at the one speed the universe does permit, the speed of light. But this shift in framing is not free. It carries a cost that no engineering can reduce, and the cost is not measured in joules or kilograms. It is measured in meaning. If an artificial intelligence, dispatched by humanity, arrives at another star system and surveys its planets and analyzes their atmospheres and maps their surfaces and transmits its findings back across 4 years of silence, has humanity arrived? The machine carries human knowledge. It operates according to human-designed algorithms. It pursues objectives that human minds defined. But no consciousness aboard that machine experiences the moment of arrival. No one looks out at an alien sunrise and feels the weight of it. No one stands on foreign ground and knows, in the way that only a living mind can know, that this is somewhere new. The data returns to Earth. The images are published. The scientific papers are written. But the experience of being there belongs to no one. The machine was present. Humanity was informed. These are not the same thing. Go further down this path, and the questions deepen. Suppose the blueprint strategy works. Suppose a robotic system at the destination receives digitized genetic information transmitted from Earth at the speed of light. Suppose, in some century far beyond our own, that system possesses the capability to reconstruct biological organisms from raw materials found in the target system. Cells assembled from local chemistry according to a human genetic template. A body built from a blueprint that crossed the void as a sequence of ones and zeros. Is the organism that wakes on that distant world a human being from Earth? Or is it something else entirely? It carries human DNA. It possesses a human genome, but it has no memories of Earth, no childhood shaped by terrestrial culture, no language learned from human parents, no experience connecting it to the civilization that encoded its design. It is born into a world it has never seen, assembled by machines it did not build, carrying the genetic legacy of a species it has never met. Information was transmitted, but information is not experience. The map was sent, but the map is not the territory. A genome is a recipe, not a person. The distance between the blueprint and the being it describes is not a gap that data transfer can close. It is the gap between knowing what a human is and being one. And even if this distinction could somehow be resolved, there is a paradox that no redefinition can escape. Communication across interstellar distances operates at light speed and light speed alone. A signal from Proxima Centauri takes 4 years and 3 months to reach Earth. A round-trip exchange, question and response, takes 8.5 years. This is not a delay that engineering can shorten. It is the speed of light applied to the distance between stars. No faster channel exists in known physics. A civilization on Earth and a presence at another star, whether robotic or biological or something in between, cannot maintain a shared conversation. They cannot coordinate decisions. They cannot respond to each other's emergencies. They cannot participate in each other's cultural evolution. Within a generation of separation, the two branches begin to diverge. Within a century, they are developing independently. Within a millennium, they are strangers. Not one civilization expanding across the stars, but two civilizations growing apart in silence, each shaped by its own environment, each accumulating its own history, each drifting further from the common origin with every passing decade. The dream of a galactic human civilization, connected by shared purpose, dissolves into the reality of isolated outposts, separated by years of silence and centuries of drift. Every space mission in human history has rested on a structural pillar that interstellar distance removes entirely. Communication. Apollo relied on real-time telemetry and voice contact with Houston. Controllers on the ground could monitor every heartbeat, every system reading, every trajectory deviation, and respond within seconds. When the oxygen tank aboard Apollo 13 ruptured, Houston diagnosed the emergency and improvised solutions in real time. The crew survived because the ground was listening. Mars rovers receive daily command uploads from the Jet Propulsion Laboratory. Engineers review each day's data, identify hazards, plan the next drive, and upload the instructions overnight. When the Curiosity rover's wheels showed unexpected wear, engineers redesigned driving protocols from Earth and extended the mission by years. The International Space Station maintains constant contact with multiple ground stations. When a coolant loop failed in 2013, ground controllers walked the crew through a complex spacewalk repair over the course of days. In every case, the mission succeeded not because the spacecraft was self-sufficient, but because it was not. The intelligence that solved the problems was on the ground. The expertise was distributed across thousands of engineers in dozens of facilities connected by communication links that operated in seconds or minutes. Remove those links, and the entire architecture of human spaceflight collapses. An interstellar mission, whether crewed or autonomous, severs those links absolutely. A crew 2 light-years from Earth cannot consult mission control. They cannot request medical guidance for an emergency that will be over 8 years before any advice arrives. They cannot report a cascading systems failure and receive troubleshooting steps in any useful time frame. They must carry within themselves every skill, every contingency plan, every piece of specialized knowledge that might be needed for the entire journey. They must be not merely astronauts, but an entirely self-sufficient civilization compressed into a vehicle. And no human institution has ever achieved this kind of total self-sufficiency. Not island civilizations surrounded by ocean, not submarine crews sealed beneath the surface for months, not Antarctic research stations at the bottom of the world, not the International Space Station orbiting 250 miles above. Every isolated human community in history has depended on trade, resupply, or access to natural resources from a surrounding environment. An interstellar spacecraft has no surrounding environment. It carries everything, or it carries nothing. There is a cost to stating all of this clearly. If the chain truly holds for crewed interstellar travel, then Earth is not a way station. It is not a launching pad from which humanity will eventually depart for grander destinations. It is home. Possibly the only home the human species will ever inhabit. Every member of our species, every generation that follows, every hope for continuation, every irreplaceable record of human culture and achievement exists on a single rocky world orbiting a single ordinary star in the outer arm of a single unremarkable galaxy. All of it in one place, all of it vulnerable to the same asteroid impact, the same supervolcanic eruption, the same slow degradation of the biosphere that could render the planet uninhabitable. The eggs are in one basket, and the basket cannot be moved. This is not reason for despair, but it is reason for an honesty that most discussions of interstellar travel prefer to avoid. There is a counter-argument, and it deserves respect. Current physics may not be the final chapter. Newtonian mechanics described the universe with extraordinary precision for over 2 centuries. It predicted the motions of planets, the trajectories of cannonballs, the behavior of tides. It was correct for every scale human beings had ever experienced. Then Einstein demonstrated that it was not correct at extreme velocities and in strong gravitational fields. The framework that had seemed complete turned out to be an approximation of a deeper reality. It is possible, perhaps even likely, that the physics we know today is similarly incomplete. That beyond the standard model of particle physics, beyond general relativity, beyond quantum mechanics as currently formulated, there exist phenomena and relationships that no experiment has yet revealed. Physics that might permit manipulation of spacetime. Physics that might allow information or even matter to circumvent the speed of light through mechanisms we cannot currently imagine. But possibility is not a plan. The existence of unknown physics is not a foundation on which to build a mission. Every barrier in the interstellar chain is rooted in physical principles that have been confirmed by more than a century of experimental evidence. Special relativity, thermodynamics, quantum mechanics, evolutionary biology. These are not speculative hypotheses awaiting verification. They are the foundations upon which every piece of modern technology operates. The GPS satellites that guide your car correct for relativistic time dilation, because relativity is not a theory in the colloquial sense. It is measured fact. The nuclear reactors that generate electricity exploit quantum mechanical principles, because those principles describe reality as it has been observed in every experiment ever conducted. To break the interstellar chain requires not merely new technology, but new physics. Physics that permits faster than light travel, or manipulation of space-time geometry, or transfer of mass without proportional energy expenditure. No experimental evidence suggests such physics exists. It may exist, but building hope on what may exist is not science. It is faith, and faith, however comforting, does not fuel spacecraft. And so we return to the beginning, not with despair, with clarity. Voyager 1 is still out there. Right now, as these words reach you, it is drifting through the interstellar medium at 17 kilometers per second. Its radio signal, weakened to a whisper after traveling for nearly a full light day, still reaches the deep space network antennas on Earth. Engineers at the Jet Propulsion Laboratory still send commands and receive responses, though each exchange now takes nearly 48 hours round trip. Most of its instruments are silent. Its power source, a lump of decaying plutonium, generates less electricity than 3 household light bulbs. Within a few years, even that will fall below the threshold needed to run anything at all. Voyager 1 will go quiet, it will continue traveling, it will not stop. Nothing in interstellar space will slow it down appreciably for billions of years. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. It will not stop there. It will not enter orbit. It will drift past unnoticed, carrying a golden record encoded with greetings in 55 languages, music from Bach to Chuck Berry, the sound of a human heartbeat, and the brainwaves of a woman thinking about love and the history of Earth. No one will play it. The distance is too vast. The silence is too deep. The record will outlast the civilization that made it by an interval that dwarfs the entire span of human history. But the record exists, and so does the dream, and so does the knowledge, hard-won and precise, of exactly why the stars remain beyond our reach. The universe did not build one wall between humanity and the stars. It built a chain: distance, time, energy, speed, radiation, dust, biology, mechanics, isolation, communication, each link forged from fundamental physics, each link welded to the next. No single breakthrough severs the chain, because no single link bears the load alone. The weight is distributed, the structure holds. This is not a locked gate with a key hidden in the future. It is the shape of the universe itself, expressed in the distances between stars and the constants that govern mass, energy, and light. The stars burn. The void stretches between them. And we, on our small world, look up with a longing that physics cannot answer, and a clarity that perhaps only physics can provide. The barrier the universe built is not cruelty. It is architecture, and understanding that architecture, honestly and completely, without illusion and without false comfort, may be the closest we ever come to crossing it. Not because understanding replaces the journey, but because understanding is the only form of contact the universe permits at this scale. We cannot walk to the stars, but we can know them. We can decode their light. We can read the composition of their atmospheres from 40 light-years away. We can detect the wobble of a planet too small to see. We can calculate whether rain falls on a world we will never touch. This is not a consolation prize. It is a capacity so extraordinary that its existence is itself a kind of miracle. A species confined to one world, orbiting one star, in one arm of one galaxy, possessing the ability to understand the structure of the cosmos from exactly where it stands. There is something strange about this. Something worth sitting with. A biological organism, assembled from elements forged in the cores of dead stars, limited to a lifespan of decades, confined to a thin layer of breathable atmosphere on a small rocky planet, has figured out precisely why it cannot leave. Not approximately, not vaguely, precisely, down to the equations, down to the energy costs in joules, down to the mass ratios and the spallation cross-sections, and the relativistic corrections that make every proposed solution collapse under its own weight. The confinement is real. The understanding of the confinement is also real, and the understanding is, in its own way, as vast as the distances it describes. Perhaps no other civilization in the universe has ever achieved this. Perhaps we are the only species that has ever stared across the interstellar void and grasped, with mathematical certainty, why it cannot be crossed by the fragile bodies evolution gave us. Or perhaps every civilization does. Perhaps on worlds orbiting stars we have already catalogued. Minds we will never meet have performed the same calculations, encountered the same chain, and arrived at the same recognition. Each one standing on its own world, looking up at the same stars, feeling the same pull, touching the same barrier, and realizing, with a sadness that transcends biology and perhaps even transcends species, that understanding may be the farthest vessel any of them will ever launch. The stars burn, the chain holds, and the knowing continues, quietly, from one small world after another, scattered across a universe that was not built for crossings, but was, for reasons no equation has yet explained, built to be understood.